Last month's MasterTech looked at troubleshooting noise, vibration, and harshness on front-wheel drive vehicles. This month, we'll look at troubleshooting NVH on rear-wheel drive and four-wheel drive vehicles. Welcome to MasterTech Release Number 6. Some of the information in last month's program also applies to troubleshooting noise, vibration, and harshness on such vehicles as the Ram pickup and Grand Cherokee. The basic principles are the same, as is the basic diagnostic approach and many of the troubleshooting procedures. As a result, it's a good idea to become familiar with the material in the March program before viewing this one. So, how is troubleshooting rear-wheel drive and four-wheel drive vehicles different? For one thing, the addition of prop shafts and transfer cases increases possible causes and frequencies of noise, vibration, and harshness. The use of prop shafts and U-joints results in different NVH symptoms than those usually associated with half shafts and CV joints. Vehicles with rear-wheel drive or four-wheel drive also may have higher than normal levels of noise, vibration, or harshness on the highway due to differences in equipment, such as tires designed for off-road use. Finally, rear-wheel drive and four-wheel drive vehicles often see more rugged use than front-wheel drive vehicles, increasing the chance of damage or wear. Since the driveline is the primary source of the differences in rear-wheel drive and four-wheel drive vehicles, this is the area we'll concentrate on in this program. Let's start with a look at prop shafts and U-joint basics. The basic job of the U-joints and prop shaft is to transmit power across changing distances and angles between the transmission or transfer case and the axles. As the vehicle is operated, a splined slip joint allows for changes in distance, while U-joints at the front and rear of the prop shaft allow for power to be transmitted at changing angles. Universal joints can allow for changing angles because the U-joint cross is able to pivot in the bearing caps as it rotates. If you've used a universal joint with a socket to tighten a bolt at an angle, you know that the joint is more resistant to turning twice during each rotation. The same thing occurs with the U-joint on a prop shaft. For that reason, the U-joints at the front and rear of the prop shaft must be positioned so that as one becomes more resistant to rotation, the other becomes less so. This is known as prop shaft phasing. As a result of phasing, changes in U-joint resistance to rotation cancel out. Proper phasing is only one part of effective prop shaft operation. Another part has to do with universal joint angles. These angles can best be understood by drawing an imaginary line lengthwise through a prop shaft and an adjacent driveline component. The angle that results is the universal joint angle, or U-joint angle. In a vehicle with a one-piece prop shaft, there are two universal joint angles, one at the front and one at the rear of the prop shaft. To minimize noise, vibration, and harshness when a vehicle is operated, U-joint angles should fall within certain limits when a vehicle is at rest. For proper phasing to occur, the front and rear angles should be within 1 degree of one another. So if the front angle is 3 degrees, the rear should not be less than 2 nor more than 4 degrees. Individual U-joint angles should also be within certain limits. These limits vary according to RPM, but for our purposes, 3 degrees is the maximum angle for U-joints at rest. It may seem odd to talk about a lower limit to U-joint angles, but the fact is that the needle bearings in the U-joint need a minimum angle of 1/2 degree to rotate and provide lubrication. Of course, just because a driveline is phased and angled properly does not mean it can't develop noise and vibration from other causes. Just as with wheels and tires, prop shafts must be balanced, and runout must not exceed certain limits. And just as with wheels and tires, at the factory, weights can be added to the prop shaft for balance. Next, we're going to look at some special checks to make when troubleshooting NVH on a rear-wheel drive or four-wheel drive vehicle. But first, let's check what you've learned with a review question. Which of the following U-joint angle limits is a concern in the driveline shown here? A, maximum individual angle, B, minimum individual angle, or C, Difference in front and rear angles. The answer is C. To minimize NVH, the front and rear U-joint angles should be within 1 degree of each other. In our previous program on noise, vibration, and harshness, we presented you with a general troubleshooting procedure to use. You can also use this approach for rear-wheel drive and four-wheel drive vehicles. But as you might suspect, there are differences in the details because of the differences in vehicle design. For example, during the preliminary inspection, you'll need to check for a bent or damaged prop shaft and for missing balance weights. Check U-joints for loose or missing clamp bolts or nuts, evidence of lack of lubrication, and worn U-joint bearings. On rear-wheel drive and four-wheel drive vehicles, it's particularly important to check motor mounts and springs. Besides creating their own symptoms, they can also contribute to driveline noise and vibration. During your inspection, also keep an eye out for any aftermarket equipment that may be contributing to NVH conditions. Oversized tires and lift kits could put U-joint angles out of spec, and extremely aggressive tread could be contributing to drone at highway speeds. If the customer complaint sounds like beat might be the problem, be sure to check for an aftermarket exhaust, which has a different resonance than factory equipment. You may recall from last month's program that beat is a modulating condition caused by the combining of two or more vibration frequencies. Just as with front-wheel drive vehicles, road testing and classifying the resulting symptoms is an important step toward isolating the cause. The wheels and tires section of service manuals for rear-wheel drive and four-wheel drive vehicles contains a chart and accompanying explanation which can prove helpful in classifying and interpreting NVH symptoms. To use this chart, you first need to determine if the vibration is mechanical, you can feel it, or audible, you can hear it. You'll also need to determine if the vibration is sensitive to vehicle speed, torque, or engine speed. The March program described a number of tests for determining this, such as the neutral coast-down test. Now, for the most part, the procedures for isolating the causes of engine speed-related symptoms on rear-wheel drive and four-wheel drive vehicles are very similar to the procedures for front-wheel drive vehicles. It's when symptoms are vehicle speed and possibly torque-related that troubleshooting is quite a bit different. As we explained in the beginning of the program, the reason for the difference is the addition of driveline components that rotate at a different rate than the axles or the wheels and tires. The difference in frequency between tires and the driveline components that rotate faster can actually help point toward the possible cause of a vehicle speed-sensitive vibration or noise. So, if vibrating wheels or tires might create a frequency of 10 hertz at a particular vehicle speed, a vibration created by the prop shaft would have a frequency 3 to 4 times that at the same vehicle speed. By becoming accustomed to the different noises and vibrations associated with different components at a particular speed, you may be able to mentally classify the symptoms produced by a road test. Later we'll cover a more precise way to classify and isolate vibration. Torque also plays a role in the classification of symptoms on four-wheel drive and rear-wheel drive vehicles. Wheel and tire symptoms are usually vehicle speed sensitive and do not require torque to be felt or heard. Driveline symptoms are also vehicle speed sensitive, but are often torque sensitive as well. The range over which vehicle speed or vehicle speed and torque sensitive symptoms occur can also be helpful in isolating the cause. For example, prop shaft frequency vibration that occurs within a particular range usually points to improper U-joint angle or U-joint damage. On the other hand, vibration from an unbalanced prop shaft usually increases as vehicle speed increases. Still, if you can't pinpoint the frequency, or if it's difficult to classify the symptom, the easiest way to isolate the cause may be to eliminate components one at a time until you narrow down the cause. Be sure to support the axles and position the vehicle at curb height if you decide to reproduce symptoms on the hoist. A vehicle's rotating components can cause serious injuries and damage your equipment, so be sure to maintain a safe distance from them. On rear-wheel drive and four-wheel drive vehicles, some symptoms point to specific areas of the driveline. For example, a low-speed knock is generally caused by worn U-joints. Differential side gear thrust washers and a worn pinion shaft bore are additional causes. Worn U-joints or excessive play in the differential can also cause a clunking sound when the vehicle is placed in gear. But there are other causes of clunking besides the driveline, such as worn or loose engine or transmission mounts, or high engine idle speed. Fortunately, the cause of most driveline clunking can usually be located by listening as an assistant places the vehicle in gear. When gear noise occurs, the first thing to check is lubricant levels in the transmission, transfer case, and differentials. Incorrect gear adjustment or wear can also cause gear noise. And if the noise occurs on turns, pay particular attention to the differential side and pinion gears. Lack of lubricant can also cause bearing noise, so be sure to check lubricant levels first. When the higher pitch of bearing noise points toward the pinion shaft bearings, you can isolate the cause to the front or rear by accelerating, then coasting. Pinion bearing noise that occurs under load points to the rear bearing. Noise that occurs during coasting points toward the front. Some bearings can also be loaded on turns. Bearing noise that occurs when a vehicle is turning points toward the axle bearing as a cause. And when turning the vehicle produces a chattering noise, suspect a limited slip differential is the cause. As we've seen, classifying NV8 symptoms according to range, frequency, or vehicle speed or torque sensitivity can help you isolate the cause. And so can associating certain types of noise, vibration, or harshness with driveline components. An additional approach on four-wheel drive vehicles may also prove useful in isolating causes to the driveline at the front or rear. On most four-wheel drive vehicles, you can accomplish this by operating the vehicle in two-wheel drive on the hoist. If the NV8 symptoms disappear with the front axle disconnected, the cause is in the front. If necessary, when troubleshooting torque-sensitive symptoms, you can use the brakes to simulate a load on driveline components. We've been discussing some of the NV8 symptoms that are created in the drivelines of rear-wheel drive and four-wheel drive vehicles. However, just as with front-wheel drive vehicles, driveline frequencies that are not a problem by themselves can also combine with frequencies from other components to create a beat problem. If prop shaft frequency does combine with the engine or exhaust to create beat, you may need to try adjusting the prop shaft angle, as described later in this program, to minimize the noise. Next, we're going to move on to using the electronic vibration analyzer to isolate the cause of NV8 symptoms, but not before you've had a chance to check what you've learned with the review question. Which of the following is most likely to result in driveline clunk when a rear-wheel drive vehicle is shifted into gear? A, tire runout. B, prop shaft balance. Or C, worn U-joints. The answer is C, worn U-joints. Both tire runout and prop shaft balance are sources of vehicle speed-sensitive vibration. As we've seen, it can be relatively easy to isolate the cause of some NV8 symptoms, such as driveline clunk. But isolating the causes of other symptoms can depend on being able to sense different driveline frequencies, or being able to associate the symptoms with certain characteristics. In some cases, you can also eliminate possible causes by removing components. But even after you've isolated a noise or vibration to, say, the prop shaft, you still need to determine exactly what the trouble is. Fortunately, there is a tool which can make isolating the causes of noise and vibration a lot easier. The electronic vibration analyzer, available through professional service equipment, can take a lot of the guesswork out of troubleshooting NVH, particularly on rear-wheel drive and four-wheel drive vehicles. The vibration frequency readout, for example, allows you to determine between vibrations created by the transmission output shaft, prop shaft, and pinion gear versus those created by tires, wheels, and axle shafts. as well as differential components that rotate at the same speed. Of course, vibration frequency readouts won't do you much good if you can't match them up with the actual frequencies of component groups. Last month, we showed you how to calculate wheel rotation frequency using tire size and miles per hour. It involves dividing vehicle speed by 5 and then multiplying the resulting 5-mile-per-hour increments by the 5-mile-per-hour rotation frequency. This frequency is obtained from the tire size chart in last month's reference book. Once you've calculated wheel rotation frequency for a particular vehicle speed, it's easy to calculate Propshaft frequency. Simply multiply wheel frequency by the axle ratio. So, suppose wheel frequency is 10 hertz at 50 miles per hour. If the axle ratio is 3.9, Propshaft frequency is 39 hertz. You can usually obtain the axle ratio from the tag on the differential housing cover. The frequency readout can do more than help you distinguish, say, wheel and tire vibrations from Propshaft vibrations. By identifying first and second order vibrations with the EVA, you can get a better idea of the actual cause. For example, first order Propshaft vibration readouts tend to indicate Propshaft runout or balance, while a second order readout points toward Propshaft angles that are out of spec. As noted previously, even when you've determined that driveline components before the differential are causing a vibration, you still need to narrow down the location to a specific component. The electronic vibration analyzer can help here too. The EVA also provides the relative strength or amplitude of the vibration at a particular location. As a result, you can easily track down a Propshaft vibration to the front or rear of a four-wheel drive vehicle, or in some cases, to the front or rear of a two-piece Propshaft. Next, we're going to use the EVA and other tools to help isolate and correct vibrations that result from a number of Propshaft conditions. Before we do, however, let's try a review question. On a truck going 50 miles per hour, wheel rotation frequency is calculated to be 12 hertz. If the rear axle ratio is 3.55 to 1, what is the Propshaft frequency at that speed? The answer is 3.55 times 12, or 42.6 hertz, which can be rounded off to 43 hertz when checking frequencies with the EVA. At this point, let's apply some of the information we've discussed to some specific Propshaft problems. After a road test produces a vibration or noise that is vehicle speed sensitive at what feels or sounds like Propshaft frequency, you can use the electronic vibration analyzer to confirm the frequency, as well as to check for the most likely location of the vibration using the amplitude readout. This can help you isolate the vibration to the front or rear Propshaft on four-wheel drive vehicles, or to the front or rear of a two-piece Propshaft. As instructed in the EVA reference guide, before testing, be sure to remove wheel and tire assemblies and brake drums. Also be sure to secure brake rotors with lug nuts on vehicles with four-wheel disc brakes. In fact, it's a good idea to consult the EVA reference guide whenever using the analyzer. During testing, be sure to check the transmission mount to make sure it's doing its job of isolating driveline vibration from the chassis. Also check the center support bearing on vehicles equipped with two-piece Propshafts. As noted earlier, Propshaft runout or balance problems can cause first-order noise or vibration that is vehicle speed sensitive, but not necessarily torque sensitive. Of course, the pinion shaft or transmission output shaft could be responsible, but the best course of action is to check out the Propshaft first, since it's a more likely cause. You can check runout by mounting a dial indicator perpendicular to the Propshaft surface. Make sure the surface is clean. On Propshafts over 30 inches in length, check locations include the center and the front and rear about 3 inches from the weld seams. Runout should not exceed 10 thousandths on the front and rear and 15 thousandths in the center. On prop shafts under 30 inches, the maximum runout is 20 thousandths at any location on the tube. If runout is excessive, repositioning the prop shaft 180 degrees relative to the pinion may bring it within specs. If the prop shaft high spot also moves 180 degrees when the prop shaft is repositioned on the pinion yoke may be responsible. The strobe function on the electronic vibration analyzer can take a lot of the guesswork out of checking prop shaft balance. As for the check of vibration, wheels and tires and brake drums should be removed. Mount the vibration sensor on the bottom of the rear axle pinion housing, facing up. The sensor input jacks must be installed in input A of the analyzer. The strobe's inductive pickup should be attached to the trigger wire near the sensor inputs. And the strobe leads must be connected to power. To be able to identify the location of the light spot, mark and number 4 locations on the shaft, 90 degrees apart. Now run the vehicle and make sure the first order prop shaft frequency reappears with the strongest amplitude. Next, press the strobe key on the EVA and select a filter range. In this case, the 35 to 45 range is appropriate. At this point, aim the strobe at the bottom of the prop shaft and note which of the marks appears there. This is the light spot on the prop shaft. An amplitude reading above 4 indicates the prop shaft is out of balance. If the reading is over 4, first attempt to minimize the imbalance by repositioning the shaft 180 degrees relative to the pinion, as described earlier. If repositioning the prop shaft doesn't bring the amplitude reading to 4 or below, you may be able to balance the shaft by installing a screw clamp with a screw positioned at the light spot. Before installing clamps, make sure the prop shaft is in the position that produced the lowest amplitude, either the original position or rotated 180 degrees relative to the pinion. If one clamp is too much weight, you may need to use 2 clamps that straddle the light spot. If one clamp is not enough weight, you may need to install another. If more than 3 clamps are needed to balance a prop shaft, the shaft must be replaced. The procedure we've described should help you correct a first-order prop shaft vibration that is vehicle speed sensitive but not necessarily torque sensitive. Second-order vibrations that are usually torque sensitive require a different approach, one that investigates prop shaft phasing and U-joint angles. As explained earlier, when a prop shaft is phased properly, changes in resistance to rotation at the front and rear U-joints cancel out. You can make a quick check of prop shaft phasing by eyeing the orientation of the prop shaft yokes. On a one-piece prop shaft, the front and rear prop shaft yokes should be oriented in the same direction. On a 2-piece prop shaft, the front and rear yokes of the front prop shaft must be oriented in the same direction as the pinion yoke. The rear prop shaft yokes must also be oriented in the same direction. It's rare for a one-piece prop shaft to be out of phase. However, if you suspect that this may be the case, there is a way to measure phasing using an inclinometer. Rotate the prop shaft so that the rear prop shaft yoke appears to be vertical. At this point, if the prop shaft has external snap rings, they must be removed from the bearing caps the inclinometer is to be placed on. In this case, that's the front and rear prop shaft caps, which are pointing down. Next, position the inclinometer on the rear prop shaft bearing cap, perpendicular to the prop shaft. Set the indicator line to 15. Then rotate the prop shaft until the inclinometer bubble is centered. Next, place the inclinometer on the prop shaft's front bearing cap. If the prop shaft is properly phased, the bubble should remain centered, within plus or minus 3 degrees of the rear. If not, the prop shaft may be twisted or damaged and should be replaced. The inclinometer is also used to measure U-joint angles. At the beginning of this program, we discussed some of the limits on the angles formed by the prop shaft and other driveline components. Improper U-joint angles can result in second-order torque-sensitive vibration and excessive bearing wear. Let's run through the procedure for checking a one-piece drive shaft. To obtain an accurate measurement, be sure to support the axles so that the vehicle is at normal curb height. U-joint angle measurements are always made from the front to the rear. So start by rotating the prop shaft so that one of the transmission or transfer case yoke bearings is pointing down. Once again, if the prop shaft has external snap rings, they must be removed from any bearing caps the inclinometer is going to be placed on. With the inclinometer on the bearing cap, center the bubble in the sight glass. On this type of inclinometer, record the number of degrees the indicator line has moved from the 15-degree position. This is the transmission or transfer case output yoke angle. You can also simply record the readings on the inclinometer and use these in calculating U-joint angles. These readings, however, will not reflect the actual prop shaft or transmission yoke or pinion angles. After rotating the prop shaft 90 degrees, take another reading at the prop shaft front U-joint bearing cap. This is the propeller shaft angle. Next, rotate the prop shaft 90 degrees and install the inclinometer on the pinion yoke bearing cap. As before, center the bubble and record the reading. This is the pinion yoke angle. At this point, you're ready to calculate front and rear U-joint angles and determine if they are within limits. To obtain the front U-joint angle, take the transmission or transfer case output yoke angle and the propeller shaft angle and subtract the smaller figure from the larger. So, suppose the output yoke angle is 2 degrees and the prop shaft angle is 4 degrees. The resulting front U-joint angle is 2 degrees. To obtain the rear U-joint angle, take the propeller shaft angle once again and the pinion yoke angle and subtract the smaller figure from the larger one. So suppose the pinion yoke angle is 1.5 degrees. Since the prop shaft angle is still 4 degrees, the rear U-joint angle is 2.5 degrees. The difference between the front and rear U-joint angles is 2.5 degrees minus 2 degrees, or 1/2 degree. The angles in the example we've just covered fall within the limits we discussed earlier in the program. The individual angles of 2 degrees and 2.5 degrees are at least 1/2 degree, but less than 3 degrees. The difference between the two angles is 1/2 degree, while within the 1 degree limit. Determining whether prop shaft angles are correct on a two-piece prop shaft is a little different. As with a one-piece prop shaft, to ensure bearing operation, each U-joint angle must be a minimum of 1/2 degree. However, with 3 joints, the canceling out that takes place with a one-piece prop shaft actually takes place at the second and third joints. As a result, to minimize vibration, the angle of the front shaft should be close to that of the transmission or transfer case, so that not much canceling out needs to take place between the first and second joints. At the same time, to yield good second and third joint angles, the front shaft should be parallel to the pinion shaft. So ideally, when you measure angles, you should find that the angle of the front shaft is very close to that of the pinion shaft yoke, while at the same time being no less than 1/2 degree or greater than 1 degree different from the transmission or transfer case yoke angle. Correcting U-joint angles at the differential pinions depends on the type of suspension you're dealing with. With front or rear leaf springs, add or remove tapered shims between the springs and axle to angle a front or rear pinion yoke up or down. On link coil front suspensions, adjust pinion angle by rotating the cam bolts on the lower suspension arms, the same adjustment as for caster. On Cherokee, use shims behind the lower suspension arm to accomplish the same thing. On two-piece prop shafts, you can also use shim stock between the center bearing and the support bracket to adjust U-joint angles. Sometimes launch shutter can persist even though U-joint angles are within specs. In such cases, on vehicles with one-piece prop shafts, try tipping the pinion yoke down 1/2 degree at a time, using shims or cam bolts. On vehicles with a two-piece prop shaft, try lowering the center bearing in 1/8 inch increments. We've covered a lot of ground this last segment. Now let's see how much you remember about a key area: calculating and analyzing prop shaft angles. Given the measurements shown here, is the prop shaft within acceptable limits? The answer is no. Although individual angles are 1/2 degree or greater and 3 degrees or less, the difference between the front and rear angles is 2 degrees, which exceeds the 1 degree limit. That wraps up this MasterTech series on noise, vibration, and harshness. This month, we've concentrated on rear-wheel drive and four-wheel drive. But no matter what type of vehicle you're dealing with, success in eliminating NVH is directly related to your understanding of how symptoms are caused and how to isolate those causes with a sound diagnostic approach. We'll see you next month.